Hello and welcome. Today we are doing linear regressions. We're going to talk about slope as a rate of change, and then we're going to do linear regressions. So first, I'm going to have you warm up with your partner or your cat or your dog or your fish or whatever pet you have or friend you have at hand, and find the equation of the line. That's the first one. Answer the question number 2, which is what is the relationship among graphs that have this equation, and answer the question number 3. So I'm going to give you a few minutes. Go ahead and put this on pause and try to answer these, and then we will give you the answers. All right, so first one is the equation of a line through those 2 points. So we know that the equation of the slope is going to be y2 minus y1 over x2 minus x1. And you're like, but Professor Adams, you told me last... Yes, I know. You can write this as, if you want, as x1, excuse me, not x's, definitely not x's on the numerator. You can write this as y1 minus y2 over x1 minus x2. It will work out the same. It's all good. So I'm going to go over here, and I told you before I like to label. So this is my x1, here's my y1, x2, and y2. So my slope is going to be 7 minus 1 over 0 minus 5. So I have negative 6, excuse me, that is a positive 6 over a negative 5, and we know that we can write the negative in the front of our fraction, so we can write as negative 6 over 5. It is fortuitous for us that this happens to be the y-intercept. I can go right to the slope-intercept form and write this as y is equal to negative 6 over 5x plus 7. So there's that one. Our next question we're going to look at is, what is the relationship among all graphs of the lines whose equation y equals mx plus 2, where m is any real number? So that's telling me my slope can be anything, but what I do know is that every single one of these lines is going to have the same y-intercept. So if I were to graph this really quick, here's y and here's x, here's 2, that every single line, so here's one line that's going to go through it, and here's another line that's going to go through it, and you have an infinite number of lines that can go through that point 0, 2. If I look at my next question, my next question says y equals negative 0.5x plus b. That means my slope is the same, but what's changing is my b. In other words, my intercept is changing. So what I have with that one is I have an infinite number of lines that are parallel or the same that are going to go through some point b. We'll call this 1. We'll call this, say, I don't know, negative 1. And they're all going to have the same slope. This I'm going to rewrite as a fraction to make my life easier. 0.5 is 1/2, so it has a negative 1/2 slope. And so all your lines are going to be parallel with a slope of 1/2. So I have all these lines that have the same slope, but they're going to have different intercepts. All right, now to the meat of what we're doing today. What we are doing today is we are talking about the slope as a rate of change. For us, we know the slope is y1 minus y2 over x1 minus x2, or the other way around. Not the other way around in terms of the x's on the numerator, it's just the subscripts can be changed. So we know that the slope then can be wrote as the change, that's delta, we talked about in a previous video, delta y over delta x. So that is the slope. So it is, when we talk about what's happening, is as x changes, so does y. So it is the ratio of y with respect to x. As x changes, this is what happens to the change in y. It is not as y changes, this is what happens to x. It is as your x value, as your input, as your independent changes, your dependent, your output changes. So that is the change. So let's take a look at what we're looking at today. We are using regression analysis to plot points, and then we're going to use regression analysis to find the equation of the line of best fit. So first, let's start with our first example. And you're thinking, but Mrs. Adams, that's not a business equation. I know that. It's okay. Most of mine will try to find business applications. This one is not, but it will work. So when you are doing this first equation, this first application, it says at sea level, the weight of the atmosphere exerts a pressure of 14.7 pounds per square inch. So we have our first ordered pair at 0, right at sea level. We have 14.7, and our units here are pounds per square inch. You may see this as PSI. As the object descends in water, the pressure increases. So the pressure P at depth D is linearly related. In salt water, we have the pressure at 33 feet. It is 29.4 pounds. So that gives us our second ordered pair. So at 33 feet, we are at 29.4 pounds. It is as you decrease in depth, the pressure increases. It is not as the pressure increases, the depth increases. No. It is as X changes, the pressure changes. As your depth changes, the pressure changes. So that's where your change, as we talked about before, let's kind of scroll up here. The slope is a change. It is the change in X as the change in Y as X changes. The X is the independent, the Y is the dependent. So we're coming back here. It says find a linear model. And you guessed it. You're like, Mrs. Adams, is that Y equals stuff? Yes. We are going to have to find an equation of this form. We're going to have Y equals mx plus b. We want to easily be able to put in values for our depth and figure out what the pressure is. So that's where we want to be. And just like my other example, woohoo, that is the y-intercept. So find our slope. First thing we do, we're going to find our slope as a rate of change as 14.7, and we're going to subtract off that 29.4. There's our pressures. Our initial depth of 0, and then at 33 feet. Now I'm going to write this out to 4 decimal places, and so I get 0.445, and that is my slope. And it's positive because I have a double negative. It will be a negative over a negative, so it'll be positive. Okay, that's not the answer for the first one. That is just my slope. Now I'm going to use that y equals. So P, and we're going to talk about, we will be talking about functions next lesson. So I'm going to just write P is equal to the 0.445, my D. I don't get to use X because they want us to use P for Y and D for depth, plus, and I get to use that ordered pair, 0, 14.7, because that is the y-intercept. So I have 14.7. Now, the second part of this question is asking me to find the depth at 70 feet. So at 70 feet, I have P is equal to 0.445 times the 70 plus the 14.7. So my pressure at 70 feet is 45.85 PSI, pounds per square inches. Now, it's asking me to find the depth at the pressure at 7 ATMs. Well, my information is all in pounds per square inch, not ATMs. So I had to go on the internet and I looked for the conversion between ATMs and PSI. And so 7 ATMs equals, and I did a conversion calculator, 102.87 PSI. Now I can use this formula right here because I'm now using the same units. That is my p-value. So this time I am doing 102.87 is equal to my 0.445 D plus the 14.7. And you guessed it, we're going to go ahead and subtract 14.7 from both sides. And after we subtract the 14.7 from both sides, we end up with 88.17 is equal to 0.445D. And of course, we know we are going to divide both sides by that coefficient on D. And our final answer is a depth of, let me put that in black, so give me a moment, put that in black, a final depth of, and I had 198.1 feet. Don't forget your units. So that tells me that 198.1 feet, I would expect to have a pressure of 102.87 psi, or in other words, 7 ATMs. If you have data points, you might be able to do a linear regression line, or you might have heard it as the line of best fit. And if you have, you would have done it probably in your statistics class, and you probably would have used the M being this lovely equation and your intercept as this lovely equation. However, for this class, we're going to go ahead and push it aside. We are not going to be doing those big equations in this class. If you're taking statistics, you get to use your statistics to do those lovely equations, and you'd have your calculator to do that. For us, we are going to do part of it with our calculator. You can either click on that link right there or copy and paste it in YouTube, and there is a video on how to put your data points into your TI-8384 and get a linear regression line. If you don't want to click on that, you'd rather read it, here is how you would get the linear regression equation, step by step, how to plot it, and how you're going to put your points in. Okay, now we're going to go ahead and do an example. This example already gave us our linear regression line equation, or a line of best fit, based on the data points. This is a chart with the data for the year 1985 to 2010 with a consumption of the fuel, fossil fuel, and this is as a percentage. So the first thing it's going to ask you is to draw a scatter plot of the data and graph the model on the same axis. Now, I could not get a screenshot of my TI-8384, so I actually did mine on Excel, because I could give you a picture of what it should look, but yours should look something like this. Now notice on the years, I have 0, 10, 20, and 30, but if I look up above on my table, I'm going to come up here to my table. If I can get up here to my table, here's my table. I have 1985 to 2010. The unit you're going to put in, or the value you're going to put in for the X's, is you're going to put in 0 for the first one. So this is the ordered pair 0, 1986. Or excuse me, 0, 86. The next one is 5, because it's been 5 years since 1985. And the next one is 10, 85, all the way down to the bottom one. And you'll just put those ordered pairs following your instructions or the video into your TI-8384, or if you want to Excel. I did the Excel. So here it is. Here's mine. Now, the slope. You can see by looking at my graph that the slope is negative. And the equation that's given to us also is negative. It is a negative 0.9. So when we are going to interpret the slope, that means as the years progressed from 1980, because that is our delta X, as our years progressed from 1985, the consumption of fossil fuels has decreased. So the negative means we have decreased. Remember, it is the change in Y over the change in X, but you talk about the X first. As the years since 1985 increased, our slope, so let me highlight that, our slope, our slope, or our line, is going down from left to right. It is negative, it is decreasing. So that's good. So let's go and finish this up on the next page. All right, so let's go ahead and finish up this example. They want us to use the model to predict the fossil fuel consumption in 2025. So the first thing I'm going to do is figure out what my value is. It's not going to be 2025, it's going to be 2025. I'm going to subtract off 1985, and I get 40 years. That's what my x is. Now remember, my equation was y is equal to negative 0.09x plus the 85.8. Okay, so that's 8. Let me erase that. That was not a very good 8. All right, 0.8. All right, so y is equal to, I'm going to put in 40 for x minus the 0.09, and then it's negative, plus the 85.8. And I'm going to put that in my calculator, and my answer is, I got 82.2. So 82.2, and that is a percent, 82.2%. So 40 years after they started collecting data, I have an 82.2% consumption. So in 2025, we should be consuming less based on this model. The last part is I'm going to use this model to estimate the first year in which the fossil fuel consumption is less than 80%. So I have, that's what y is. My output is 80, and I'm trying to find a value for x. So I have 80, and then I have negative 0.09x plus the 85.8. I'm going to subtract 85.8 from both sides. And this side we get a negative 5.8. And go back to the black, 0.09x. I'm going to divide both sides by that negative 0.09. Again, because when I'm solving for linear equations, my goal is always to have a leading coefficient on x to be 1. And so my final answer is in 64.4 years after 1985, we should have, based on that data, an 80% consumption or less of fossil fuels.